Ready or not, here comes science. They might be giants, here comes science.
Hello everybody and welcome. Today we are going to be talking about another very exciting aspect of science. And today's topic is actually just a little bit about quantum physics, believe it or not. But mostly we're going to be talking about visual light, okay, as part of what's known as the electromagnetic spectrum, okay. So the electromagnetic spectrum is just a way of splitting up all of the different energies that at least we as humans know of currently in the universe. Okay, and it's actually listed from lowest energy up to highest energy. And it goes first radio waves, second microwaves, third infrared, fourth visible light, fifth ultraviolet, sixth X-rays, and seventh gamma rays. Okay, so that basically means that radio waves have the lowest energy, which means that they actually have a very long wavelength. And gamma rays are the exact opposite. They have an extremely high amount of energy and very small wavelengths. Okay? So you all know that X-rays and gamma rays are used a lot in medicine. Okay, we've got gamma rays for radiation therapies for cancers and things like that, and of course X-rays to look at bones and things of that nature. Okay? But today we're actually going to mostly be talking about the visual spectrum. Okay, I'm sure that you guys have all seen rainbows, you know about prisms, all that kind of thing. Okay, now the visual spectrum, at least for us, is made up of 7 colors that go in a specific order. And it's always remembered, like if you go to grade school and all that kind of stuff, then you always remember it by Roy G. Biv, R-O-Y-G-B-I-V. That's how you remember the order of the colors: red, orange, yellow, green, blue, indigo, violet. When you list them like that, that's actually listing it from the lowest energy to the highest energy. Okay? Just like going radio waves to gamma rays. The only thing is that you have to remember the visual spectrum, the spectrum that we can actually see as color, is a very, very, very tiny part of the entire EM spectrum. Okay? But it's pretty much all that we know. So it's something that has been studied for years and years and years and years. Okay? Now, the way that we're going to demonstrate this, at least just a little bit, is with fire. Because fire uses visual light. It gives off visible light. Okay? And it gives off several different colors. But they are very specific colors depending actually on the temperature of the fire. It makes sense. The higher the temperature, the more energy that you're going to have, so you're going to be closer to the blue and the violet end of the spectrum rather than the red and the orange and the yellow. Okay? So what I have here are a couple of lighters. Okay? We've got a barbecue lighter and a regular hand lighter. Now, these are both butane lighters. Okay? And if we light these up, then we can see our little flame. Okay? Same thing with this guy. Right? Now, you notice the flames look pretty much identical. Okay, it's a nice orangish reddish. But if you look really close at the very base, particularly of our butane lighter or of our barbecue lighter, you can see there's just a little bit of blue in there. That's because the blue is the hottest part of the flame. Since it's hotter, it has more energy. To demonstrate this a little bit better, I have another lighter here. Well, not necessarily a lighter, but this is actually a creme brulee torch. Okay? And when we light this up, this actually burns much hotter than either the barbecue lighter or the normal lighter. Okay? But the interesting thing is this actually still uses butane. It just burns it at a much hotter temperature. So when we light this, nearly the entire flame is blue, which means that this flame has much, much, much more energy than the flames from our barbecue lighter and the just regular hand lighter. Okay? And that's why this is a torch rather than a lighter. Same thing if you look at welding torches, oxyacetylene, all that kind of stuff. You see more blue flames versus red and orange flames because they're hotter. Okay? They just have a lot more energy. Okay? Now, for this next part, I'm actually going to go and shut the lights off to make it a little bit better. I know that you guys can't see me, but trust me, I'm actually here. And what we're going to talk about now is how light is made up of different colors. I'm sure that a lot of you have heard of something called white light. White light is called that because it's made up of all 7 colors of the rainbow, if you guys remember that Roy G. Biv. Okay? And what I'm going to do is I'm going to use a prism to split light into its component colors. Okay? I'm sure that you all know one of the most famous images of a prism from Pink Floyd's album Dark Side of the Moon. That is actually how it looks when you have a prism. So what I've done is I've actually taped a prism, or in this case a diffraction lens, onto my camera lens. And what I'm going to do is I'm going to use the light on my phone to show you what it looks like when you view it through this diffraction. So, I've got my phone in my hand here, and I'm going to reveal it to the lens. Now, sorry for that giant bright spot there, but if you guys notice, we have all sorts of diffraction going on from our light. This is actually the flashlight feature of my phone here, and what you can see is we have almost a starburst pattern of rainbows. And you guys can see at the very ends, we see that red, and then you can barely see the orange and the yellow, but then you see green very clearly, and blue, and some violet at the very tip. Okay? For those of you uninitiated, the violet is actually purple, and indigo is sort of a combination between violet and blue. Okay? So what we're seeing is the breakup of this light. Okay? Normally, when you just have white light like this, then all that you see is white. But when we look at it through this awesome diffraction lens here, it splits up the light into all of these component colors. If you were to look at say different colored bulbs, for example halogen bulbs from cars and things like that, that are either blue or maybe orange or green or even purple, then you would not see all 7 of these colors. You would only see a subset of them. The reason being, they're not all there. In this case, remember, this is white light. Since it's white light, it has all 7 colors. Okay? So the next thing that we're going to discuss very briefly is going to be ultraviolet light. I happen to have here an ultraviolet light that I'll show you after I take my little lens off here. So, there we go. So if you'll recall, ultraviolet light is actually used very frequently by crime scene investigators to look for blood and other various bodily fluids at crime scenes. The way that it works, especially with blood, is you spray it with a substance called luminol. After blood has been sprayed with luminol, the cells light up under the black light. And that's how you find out if there's blood or other bodily fluids of various sorts. Okay? And in this case, I've got a pretty standard stick black light right here. Okay? Now you notice that only certain things are really visible under this black light. For example, you can't really see my face very well. The reason is actually very simple. When you look at a black light, you are not seeing the light. If you remember, ultraviolet light is outside of our visual spectrum. Our visual spectrum is only those 7 colors, okay? And ultraviolet is a more powerful one that's on the very far edge, just past violet, obviously. That's why it's called ultraviolet, okay? And what we're actually seeing here are the reflections of the ultraviolet light off of different surfaces. For example, my shirt is a white shirt, so you can see it very well under black light. It glows really well. Same thing if you have things that are like neon and things of that nature, they glow extremely well. Excuse me. You'll notice that some of my games on my shelf back there are also glowing very nicely too. But it's mostly the UPCs and any games that have white lettering. For example, right there we've got Labyrinth. Great game, by the way. So, what we have here is a black light that causes reflections for us to see. Unlike some animals, particularly, we can talk about bumblebees. Bumblebees can actually see ultraviolet light. Sorry. Bumblebees can actually see ultraviolet light. They see it coming off of flowers, and that's how they know where to go, or that's at least part of how they know where to go. We can't see the UV light, but we see nifty little reflections off of it or from it, okay? And we use it in many, many different capacities. If any of you have ever gone tanning, this is the light, okay? But do be careful. Ultraviolet light is dangerous. It can actually damage your DNA, all right? And we don't want damage to our DNA, do we? No, we do not, all right? So, that's it for me with ultraviolet light. Now, just hang on 2 seconds. I'll be right back. All right. So, that's it for me in our little discussion about light and a little bit of quantum physics. I hope that you all really enjoyed it, and I hope more so that you learned something. And with that, I will say goodbye for now, and I'll see you next time.
I'm so into